Hi everyone, my name is Matt, and I'm going to briefly talk to you about reinforcement learning and applications to electronic design automation. In general, machine learning can be clustered into three types. First, there's supervised learning, where given some input, you're trying to predict an output. So think of, tell me what the price of this stock will be tomorrow, or maybe a category, tell me whether this stock will go up or down. Then there's unsupervised learning, where you're just trying to understand the data, maybe find anomalies like credit card fraud. And finally, there's reinforcement learning. And this is a different paradigm where you have something, some kind of agent that can go and interact with an environment. So it can do that by taking actions, and it can take actions depending on the state it's in, where it is, what it sees, in order to try to maximize some long-term reward. So today I'm going to talk a little bit about reinforcement learning and why that's a tool you should know about. In RL, there are no right or wrong answers. When the agent does something, it's never told, oh no, that wasn't correct, you should have done this. Instead, the agent has to learn over time what to do. What does right mean? As the agent is interacting with the world, this can have some cost. So either this is a simulation and it just takes compute time, or it could be the real world where there are real world costs. So for instance, if you're trading stocks, you can lose money. If you are getting robots to learn to do a task for you, there can be wear and tear on those physical robots. Supervised and unsupervised learning has had many successful applications in real world problems. And for many years, reinforcement learning was kind of thought of this toy problem or toy approach. And a lot of the results in reinforcement learning have been in games, so things like Dota and StarCraft or Go. However, there are more and more successful uses of RL in robotics or in data center cooling, or I was lucky enough to get to work with Royal Bank of Canada on stock trading. But for all of these tasks, the reason RL is an appropriate method is because they are sequential tasks. You have to make decisions over time, and the decisions you make change how the world acts. So it's not just you make a single decision and you're done, but instead, for instance, when you're playing chess, you have to make moves, and those moves change the state of the board. And what happened in the past is going to influence what you're seeing now. Similarly, in robotics, in AlphaGo, in stock trading, we never know what the right answer is. We never know the optimal thing to do. Instead, we have to try different approaches, try different things, and then over time understand what's better. Now, this is great because it means that we're able to solve problems that we don't necessarily know the right way to solve. The drawback, as again I'll discuss more in the longer talk, is that this can be time and compute intensive. So there was this TRIPS project, which was this novel architecture, and there was a scheduler built. And you would go from the source code into a data flow graph, and then given the data flow graph and the topology, you'd have to come up with a schedule. So there are 4x4 tiles, so there's 16 tiles, and there you can put up to 8 instructions on each tile. So you have to figure out, given my data flow graph, which of these up to 128 factorial scheduling possibilities do I want? So I need to place all of these instructions onto these generic functional unions. Instead of directly learning the scheduler, instead we learned a heuristic, so that we could go and analyze the different instructions in the data flow graph and come up with a heuristic which the scheduler could then use to help figure out what to place where. We defined our state in terms of 11 features, so 11 state variables that had to do with which instruction was I placing now and what has already been placed. The action is going to be, where do I actually put this instruction? And the reward is actually 0 until all of the instructions are placed. Once I've placed up to 128 instructions, then I can actually run the thing and see if there's a speed up. If you'd like to get in touch, you could learn more about my research group, irll.ca, the Intelligent Robot Learning Lab, or you could reach out to me through AMI, the Alberta Machine Intelligence Institute,